Okay, we have a lot to get through, but all of it, I'm sure you will agree, fascinating. Um, what we want to do is to develop a sense of magnetic field strength. We'll start with electric field strength, which you may or may not recall was developed as the intermediary between two charges. That you have a charge, it creates an electric field, and then that field acts on the second charge. That particle physics, of course, they would say there was an exchange of a virtual photon, that in fact if you have a charge it creates a region of virtual photons which grow more and more scarce as you go out, but we don't need to deal with that. Here's the idea of an electric field, capital E, and so this idea of a magnetic field, capital B, will be the same thing. It will be the intermediary, the vehicle that transports force, this time between two currents. That if you have a current, it gives rise to a magnetic field, and that magnetic field will then exert a force on a second current. You may or may not recall the name Ørsted, the Dane who realized that when current flows, a magnetic field arises. Okay, so here was the definition of electric field strength, where I put the subscript 1 to represent that this is the field from charge 1, and then you put a charge 2 into that field. A force arises, you divide out the second test charge, and that is what we mean by field strength. Well, exactly the same thing will be our definition of magnetic field strength. That this time it is a matter of a current times the field strength gives rise to force. Here it was a charge, and charge of course was a scalar. Current is a vector whose direction is given here by this vector quantity v. Well, we're multiplying two vectors together, and the result is going to be a vector, so we need to take a vector product, also known as a cross product. Recall with a cross product the importance that you get the order right, that it is not a commutative operation. Recall also that when you do a cross product, you start with your fingers pointing in the direction of this vector, then turn your wrist until you can wrap into the direction of that vector, and your thumb points in the direction of their product. That is a direction that is perpendicular to the plane formed by these two vectors. Well, what that means is that if these two are completely parallel, then there will be no force. Similarly, if the charge is 0, then you don't have any current. There would be no force. If the velocity is 0, you have a charge but it's not moving, there will be no force. But that force, when you get it, is going to produce an acceleration which will change this velocity. But note that the force is always perpendicular to the velocity, so it will never change the magnitude of the velocity. It will never change the kinetic energy. It will only change the direction and cause it to go in a circle, as we we'll see in a subsequent slide. The sign of this charge matters. If you have a negative charge moving in the direction of this velocity, then you go ahead and do the cross product, get the force, but the fact that this is negative means that the direction is the negative of the direction that the cross product gave you. I hope that will become clearer as you do the checkpoint problems. Finally, the units of magnetic field, which are indeed Teslas, but notice I need something whose units, when you multiply it times coulombs meters per second, gets you newtons. So clearly units of B are newtons, and all of this is in the denominator, coulometers per second. but a coulomb per second is of course an amp. So usually we say that a Newton per ammeter, both of these in the denominator, is what a Tesla is. That may seem like trivia to you. We will come back to it many times. I want you to be able to figure out what the dimensions of a Tesla are, and the way you do that is go back to the equation which defined magnetic field strength. Okay, here is your checkpoint. It is just a matter of applying the cross product. You start with your fingers of your right hand pointing the direction of V, and then turn your wrist until you can wrap them into the direction of B, and your thumb points in the direction of the force. But pay attention to whether it is a positive or a negative charge that is moving with that direction V. If it is negative, then you take the negative of the direction you get from the cross product. The Hall effect, new topic. If you have current, boom, flowing in a magnetic field, then there is a force. Suppose the charge carriers in this wire, which is carrying current downwards, we are getting there, were positive charge carriers. Suppose a current downwards meant positive things going downwards. Well, then V would be downwards. Q is positive charge. You hold your right hand pointing downwards and turn your wrist until you can wrap your fingers away from you into the X's, and you can see that your thumb is pointing to the right, which means this force, which is the force on the charge carriers, is going to push them to the right. But if the charge carriers were negative, this is still a current going downwards, but suppose that meant negative charge carriers going up. Okay, you take your right hand, point it up, then turn your wrist, which shouldn't be very much turning, so you can wrap your fingers away from you as the blue X's, and your thumb is pointing to the left. But these are negative charge carriers. Negative left is also known as right, that they will be pushed to the right. So all we need to do is take a voltmeter and find out whether the right-hand side of this wire with current going down is a high potential or a low potential. And it turns out it will be a low potential, which is proof that the charge carriers are electrons, despite what Ben Franklin may have said, and despite all the conventions of physics. There's something called a Hall effect magnetometer, and what it does is uses a voltmeter. It looks at how much potential difference there is between the sides, and from it gives you a readout for how strong the magnetic field is. Didn't I say this stuff would be cool? Oh yeah. Okay. This was an experiment done by J.J. Thomson in 1897. It is often credited as the discovery of the electron, but what it really did was find out what the charge-mass ratio of an electron is. So you have this evacuated tube. Here goes to a vacuum pump, and then you have a filament here, which we use this circuit to make it hot so that electrons boil off of it. But we make sure that it is electrons with this circuit here, which makes this be the high potential anode and this be the low potential cathode. Indeed, this evacuated tube is known as a cathode ray tube. And here is the cathode ray. These electrons, when they boil off, are accelerated through the vacuum towards the anode, and those that pass through the hole become a cathode ray. Then we send them through this region where I have an electric field, the purple arrows. You can see we have a high potential plate on the top and a low potential plate on the bottom, so the field is down. And also a magnetic field, which is produced by a solenoid. We don't have that shown to us here, but the magnetic field is going away from us. I would like you to use your right hand rule and on your worksheet indicate What direction will this electron beam be pushed by the electric field going down? What direction will this electron beam be pushed by the magnetic field going away? And here's a little hint. If you don't get different answers to those two questions, you've done it wrong. So, what we do is turn on the electron beam. The electrons hit this screen and they scintillate. They fluoresce, and the electron's energy becomes light when they are stopped here. We then turn on the electric field, and that causes this beam to move either up or down. One of those directions you gave. And then we turn on the magnetic field and we increase its strength until we get this beam back where it was before it was deflected by the electric field. And then we do these calculations. We don't need the bottom of that. No more. Okay. So the force from the electric field, and notice this is force here, even though the E kind of grabs your eye. This is force. It's equal to the charge times the field strength. And so the acceleration, this is acceleration, it's not E, it's acceleration, would be that force divided by the mass. Fact, just let it wait. And then the time that it takes to get across this region is given by the length of the region divided by the velocity with which it crosses. Now, we take those two ideas and consider this event when the electron beam is turned on and it causes the beam to move upwards, some amount delta y. And that's equal to the initial y velocity, which is 0, plus 1/2 the y acceleration times time squared. Ah, but the acceleration is this value, and the time is this value. Ooh, looking ugly. And then we adjust the magnetic field to cancel out that delta y, so that the force pushing it up or down is the same as the force pushing it down or up. Thought I'd give it away, didn't you? At this, the force from the electric field is this. The force from the magnetic field is this. Notice I use a Q instead of an E, but it doesn't matter. When we divide by QV, no, we divide by QB, here we go, and notice there was a perpendicularity between the velocity and the magnetic field, so I don't need to deal with that cross. Then we take this value for V and we put it back into this equation. And it ends up looking like this, trust me. And then you can solve for E over M by moving everything over here with the delta y, which looks ugly, but all of these values could be determined. And so J.J. Thomson was able to discover the charge-mass ratio. You are going to do something very similar to this in a later lab. You send a beam of electrons into a magnetic field going away from you. What's going to happen? They're going to be pushed. And if you take your hand and point it to the right, and then turn your wrist until you can wrap your fingers into the page, you see your thumb is pointing up. But these are electrons, so it's negative up. That's called down. So this thing is pushed down, which causes it to be going in a new direction. But then that is pushed perpendicularly, new direction. It is constantly pushed perpendicularly. It never changes the magnitude of the velocity, but the direction changes always with an acceleration perpendicular to the motion. That is the recipe for a circular path. And that is indeed the path that you get here in the magnetic field. But wait, there is more. Consider a circular path. you've got centripetal force coming from that interaction of the current and the magnetic field. So I can solve this for R. Yeah, looks bad, Mr. Horton. And then let's talk about the period. This is not T for Teslas. This is the period, the time it takes to go around the circle once. That, of course, is equal to the distance that it goes, one circumference, divided by the velocity. Ah, but I will substitute this value for R. 2 pi times that value divided by V. And look, the V's divide out. This is a very nice result. The period, the time it takes to get around the circle once, does not depend in any way on how fast it is going. And so it will go around a circle. Now, if you make it go faster, it'll go around a bigger circle. If you make it go slower, it'll go around a smaller circle. But the time it takes to go around the circle is independent of its velocity. Very important for the next slide. But before we go on, here you have a beam of electrons that are in a fluorescing medium so that we can see them, and the force is towards the center. The velocity of the electrons is that way. So you tell me, what is the direction of this magnetic field? And of course, if they were protons, then the magnetic field would have to be in the opposite direction to get this kind of force with that kind of velocity. Well, this fact that the period is independent of velocity is used in a cyclotron. This is a picture of the original cyclotron, about 10 centimeters across. Little teeny thing. You could hold it in the palm of your hand. It was developed by a team led by Dr. Lawrence in 1932. Same Lawrence that Lawrence Livermore Labs is named for, out at Berkeley. And it consists of these two metal cavities. We call them Ds because they look like Ds. And then you get a charge going. And of course, the charge will be experiencing a magnetic field, which is made by something else, not shown here. And that magnetic field causes it to travel in a circle, continues to cause it to travel in a circle here, but here it is not inside a D cavity. This D cavity is positive, this D cavity has low potential, and so the electron, when it leaves the cavity, gets accelerated across that gap. While it is inside the cavity, it is, of course, does not experience any field. Inside of a metal charged cavity, there is no field. But it gets accelerated here, and then it goes through approximately half a turn, by which time I have changed this D from being the high potential one, and now this one is the high potential one, so the electron gets accelerated across that gap. And then it goes through this arc. Now it is going faster because of that acceleration, but it takes exactly the same time. And by the time it gets to here, I have changed this to be the high potential, so it gets accelerated there. It keeps going around, going faster and faster, but the rate at which I change which one of these is positive and which one is negative stays the same as it goes out and out. And so that electron gets accelerated up to a very high rate of speed, and then I deflect it and bring it out. And with 1800 volts, not that extreme amount of voltage, that Lawrence was able to give, what I've got is hydrogen protons, so he was doing a hadron accelerator. He was able to take protons and accelerate them to 80,000 electron volts, which means they were going at 100th the speed of light, which is not too shabby. That's very fast. Good job, Dr. Lawrence, you've done it again. Okay, again, this notion of the magnetic field causing things to go in a circle. But if you were to project a charge, in this case a positive charge, at this angle, and you had a magnetic field going that way, this velocity would have two components, one of which is parallel to the magnetic field and would not have any force arising. And so the vertical velocity would stay unchanged, but the horizontal velocity is perpendicular to the magnetic field. And so if you do a cross product, this is a positive charge, I point my right hand in the direction of V, turn my wrist until I can wrap into the direction of B, and my thumb is going into the page. It will be caused to curve in a circle going this way. A circle plus that constant vertical motion, and so it goes in a helix, spiraling. Well, here you have a curiously shaped magnetic field, and the charged particle moving in this direction will be caused to move in a helix, but here there's going to be a net force on it that moves it towards the center of this bulge. But once it crosses over to this side, there is a net force that moves it back to the center of the bulge. And so this curiously shaped magnetic field has the property of keeping charged particles inside. As they go this way, they helix back into the center. As they go that way, they helix back into the center. We call this a magnetic bottle. And when they try to cause fusion, they have to hold a bunch of particles in a small space, and then we hit them with lasers to make them very hot, but there's nothing that can hold them there because they are so very hot. So what we hold them in is a magnetic bottle. Here is another magnetic bottle. It is produced by the curiously shaped magnetic field of the Earth. Not so curious. And when charged particles come through space, either from the sun or other cosmic sources, the positively charged particles spiral about this magnetic field, and they get concentrated at one end, let's say the North Pole, and negatively charged particles spiral about in the other direction, and they get concentrated at the South Pole. And this very ionized material passing through the atmosphere excites the atmosphere and causes it to glow with a sort of a spectral emission, and these of course are the auroral lights. At the North Pole we call them aurora borealis, at the South Pole aurora australis. But now you know where they come from. Oh, physics, it's wonderful. Okay, give you another checkpoint. You do that thing. Another checkpoint. This has two parts, A and B. You do them both. Did the other one have two parts? No. Yes, it did, A and B. But what I did was I combined them. No, here's A and here's B. Yes, two. And finally, this is the cherry on top. Here is the coup de grace. No heads will get cut off. The creme de la creme. This is Einstein, when he wrote in 1905 his famous paper which established special relativity. The actual name of that paper was On the Dynamics, the Electrodynamics of Moving Bodies. Actually, that's not true. Its name was Zur Elektrodynamik bewegter Körper. Bewegen is to move. Körper or bodies, of course that's electrodynamics. Oh, I can read German. But what is electrodynamic about special relativity? Well, consider this wire which is carrying current to the right, which we know in fact means that electrons are going to the left. But for the sake of this discussion, it would be useful to also have positive charges moving to the right. Usually we don't talk about them as protons, but rather as holes. An electron going to the left is the same as a hole going to the right. Here we have a, oh, that wasn't supposed to be there. We have a positively charged particle. And of course, this positively charged particle will perceive a neutral wire. There will be no force on that charged particle. Indeed, a static charge does not get any force from a current-carrying wire, because the current-carrying wire is always neutral. Marbles in a tube. But if this particle is moving, then that's a current. And currents are supposed to feel the magnetic fields from other currents. In the reference frame, oh, now we're talking special relativity. In the reference frame of this charged particle, these two velocities would not be the same. This velocity would seem to be bigger, and this velocity would seem to be smaller. And you recall from our discussion of special relativity that an object moving faster has time dilation and length contraction. And it is the length contraction that most interests us. That because the negative charges are moving faster, they will be more length contracted than the positive charges, which are moving slower. And this effect leads to a net negative charge here. And so this positive charge is attracted by that net negative charge. That as some of you were trying to say last year, that magnetism doesn't really exist. Magnetism is a relativistic effect of the fact that there is a current moving, that the charges are moving. So it's actually electrostatic arising from this relativistic effects. That's kind of cool, and it's pretty useless that we're going to go on talking about magnetism like it really exists, because it makes your life much easier. And there is an effect that exists, but it's, according to special relativity, it's an electrostatic effect caused by this relativistic warping of space. And that's all. Thank you, my friends.